Welcome viewers to the third lecture for the online series of lectures for the course of Algebraic Topology 2. In the previous lecture, we studied the concept of reduced homology in fair detail. Um, we will we plan to study relative homology in this third lecture. Uh, First of all, from a very informal point of view, we'll study a few examples. We'll state the excision theorem and also prove it. Then we will prepare the background materials to deal with the homological problems from a very formal point of view uh, through axiomatic approach. These axioms are called Eilenberg-Steenrod axioms. Okay, so without wasting time, let me get started with the definition of relative homology. Um, so we start with a simplicial complex and a subcomplex of it. Okay, so we'll be studying relative homology. Relative homology. Suppose K is a complex, is a given complex, and K0 is a subcomplex of K. Then the group of P chains on K0 can be seen to be a subgroup of the group of P chains on the complex K. Okay, any group element, in fact, element in this group of P chains on the subcomplex K0 can be seen to be a group element of here in the following way. If small c sub p is a P chain on the subcomplex K0, one extends it, this group element or P chain on K0 to be a chain on the whole complex K by letting its value be 0 on each oriented P simplex of K that is not in the subcomplex K0. Okay, this way one sees that an element of this group can always be seen to be an element here. Okay, which shows that Cp of K0 is a subgroup of Cp of K. Now, since Cp of K0 is a subgroup of Cp of K in the above mentioned way, it makes total sense to talk about the quotient group. Cp of K modded out by Cp of K0. Okay, one can talk about this quotient group. Now, let me give you the the formal definition of a relative p-chain. Definition: if K0 is a subcomplex as before, subcomplex of K, the quotient group Cp of K modded out by Cp of K0 is called the group of relative p-chains, of K modulo K0. Okay. Relative p-chains of K modulo K0, and is denoted by Cp of K comma K0. Okay. All right. Now a remark about the basis elements here. In fact, this guy is a free abelian group. Remark: the quotient group Cp of K comma K0 is free, for it has basis as basis all cosets of the form sigma I. Okay, Cp of K0. Okay, where sigma I is an elementary p-chain corresponding to the oriented p-simplex. Oriented p-simplex sigma I of K that is not in K0. That is not in K0. Okay. 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 And so a basis element here is going to be something like this, right? Where C sub p is an element here. Okay. Good. Given the boundary operator del P that takes Cp of k to Cp minus 1 of k, it its restriction to the subgroup Cp of k0 to Cp of k0 is denoted by the same symbol for convenience, is denoted by the same symbol for notational clarity, del P. Cp of k0 goes to Cp minus 1 of k0, okay? They are both represented by del P. These two homomorphisms induce a homomorphism between the relative chain groups, okay? These homomorphisms induce a homomorphism which we are going to denote by the same symbol del P. Homomorphism del P from the group of relative p chains on k modulo k0 to the group of relative p minus 1 chains on k modulo k0. Okay. So, explicitly by this, sigma I plus Cp of k0, which represents an element here, and that goes to, under this homomorphism, that goes to del P sigma I plus Cp minus 1 of k0. Okay, good. So I leave it as an exercise for you to check that as before it satisfies the boundary operator for the relative chain groups. This satisfies del P composed with del P plus 1 is equal to 0. Okay. Now, about relative cycles, relative boundary, and relative homology group. We let Zp of k comma k0 to be the kernel of that boundary operator del P, where del P is this guy, is this operator that takes Cp of k comma k0 to Cp minus 1 k comma k0. Okay. That's Zp of k comma k0. Now Bp of k comma k0 is the image of delta p plus 1, where delta p plus 1 is the boundary operator that takes Cp plus 1 k comma k0 to Cp k comma k0. And the homology group, the respective homology group, is given by the quotient of Zp of k comma k0 by Bp of k comma k0. Okay. So there are three groups. This is a group, this is also a group, and this is a quotient group that one obtains using these two groups. These groups are called respectively the group of relative p cycles the group of relative p boundaries relative p boundaries and the relative homology group of K modulo K0 in dimension P. Okay, now a small remark on the relative P cycles and relative P boundaries of K modulo K0. Remark: a relative P chain C sub P, small c sub P, belonging to the group big C sub P K comma K0 being a P chain on K, okay, is this guy is a relative P cycle, relative P cycle that is C sub P is in ZP of K comma K0 if and only if del P CP is carried by K0. Okay, so instead of claiming it to be 0, we are claiming that this guy is carried by the subcomplex K0, and only then we say that uh, this guy C sub P is a relative P cycle of K modulo K0. Furthermore, this this guy C sub P is an element of BP of K comma K0 if there exists a P plus 1 chain D sub P plus 1 on K such that the difference between C sub P minus the boundary operator del P plus 1 acting on dP plus 1 is carried by K0. Again, here we don't want it to be exactly 0, but we want it to be carried by the subcomplex K0. And then we say that it's a relative P boundary. Okay, good. Now a bunch of examples. Let me get started. Let me erase everything and get started with the first example. Example 1. Let K consist of an n simplex, okay, and its phases. Okay, so that's the underlying complex. Let K0 be the set of all proper phases of K. Okay, which means that K0 is an n minus 1 dimensional complex, right? Since K is the n simplex together with all its proper faces, K0 is going to be and K0 is taken to be the union of all its proper faces. K0 has dimension n minus 1. Now consider the group of p chains of k modulo K0, Cp of k comma K0, which is this quotient group Cp of k modded out by Cp of K0. Okay, if this p is greater than 1, the dimension of the dimension of the complex k, okay, then Cp of k is obviously trivial, meaning that Cp of k vanishes, right? And since Cp of k vanishes, this also vanish. This also vanishes, and in other words, this guy is trivial. So Cp of k is trivial, making Cp of k comma K0 is equal to 0. Okay, so this is the story when p is greater than 1. If p is less than n, so this is the story when p is greater than n. In other words, p is greater than the dimension of the underlying complex k. Now if p is less than the dimension of the underlying complex k, then it can be immediately seen that Cp of k coincides with Cp of K0. Okay, so the group of p chains on k coincides with the group of p chains on K0, so that since this and that are the same, this quotient group vanishes. Cp of k comma K0 is equal to 0 again. Okay, so we thus have seen that Cp of k comma K0 is equal to 0 unless p is equal to n. Okay, when p is equal to n, Cn of K0, right? Since K0 is an n minus 1 dimensional complex, Cn of K0 is trivial. So that Cn of k comma K0, this group of relative n chains on k modulo K0, is equal to simply Cn of k, right? Since this guy is trivial. Okay. Note that Cn of k, the group of n chains on the complex k, on the n dimensional complex k, which consists of an n simplex together with all its faces. This is seen to be free abelian. We know that this group of n chains on an n-dimensional complex consisting of a simplex and its faces is free abelian. In fact, it's infinite cyclic, right? It's isomorphic to Z, generated by the elementary n chain sigma corresponding to the n simplex hence Cn of k is isomorphic to Z. Okay, so therefore we see that Cn of k comma k0, the group of relative n chains on k modulo k0, is isomorphic to the additive group of integers. Okay, all right, so that closes the story of the group of relative p chains on k modulo k0. Now, since Cp of k comma k0 is equal to 0 for all p not equal to n, one has this sequence. 0 goes to Cn k comma k0, right? So this boundary operator is del n plus 1, and this boundary operator is del n, and this is 0 also, okay, because of this. So that from this sequence we see that kernel of delta n, okay, so kernel of this map is Cn k comma k0, which is everything here, and image of delta n plus 1 is supposed to be trivial, since delta n plus 1 is a homomorphism. So under this map, 0 is mapped to just 0. That's the only possibility. So resulting in kernel of delta n modded out by image of delta n plus 1 equal to Cn of k comma k0, right? Since image of delta n plus 1 is trivial, so kernel of delta n quotiented out by image of delta n plus 1 is just the group of relative n chains on k modulo k0. Hence, one immediately finds that the relative relative nth homology of k modulo k0 is equal to Cn of k comma k0, and we have seen earlier that Cn k comma k0 is isomorphic to Z. Okay. Also, since Cp of k comma k0 is trivial for all p not equal to n. The group of relative p cycles zp of k comma k0 of k modulo k0 being a subgroup. This guy is a subgroup of this guy, subgroup of a CP of k comma k0 is also trivial, right? Is also trivial, leading to the fact that HP of k comma k0 is equal to ZP of k comma k0 modded out by BP of k comma k0 is equal to 0 for all p not equal to n. Okay, the relative homology group vanishes. Okay, so let me summarize what we have gotten so far. To summarize, the case of the complex K consisting of an n simplex and its faces, and K0 being the set of all its proper faces, one obtained the following: HP of k comma k0, which is the pth the uh, the relative homology group of k modulo k0 in dimension p is equal to 0 for all p not equal to n, and Hn of k comma k0, the relative homology group of k modulo k0 in dimension n is isomorphic to z. Okay, so this is the result. Okay, this was example 2. Now let me give you another example of relative homology groups. Example 2, where we let k be a complex, any complex, and let v sub alpha 0 be a vertex of the complex K, right? First, we are interested in informing the relative homology group of K modulo V sub alpha 0 in dimension 0. Okay, this is what we are interested in. But before that, let us try to address what C0 of K comma V alpha 0 is. Okay, the relative zeroth chains of K modulo the vertex. What is this group? Since C0 of K comma V sub alpha 0 is the quotient group of C0K modded out by C0 of V sub alpha 0. An element here C sub 0 K comma V alpha 0 can be written as sum of n alpha v alpha, where alpha is not equal to alpha 0, because we are modding out this part, this subgroup. Okay, sorry, this is v alpha. This is going to be v alpha, where alpha is not equal to alpha 0, where v alpha is not equal to alpha 0 is a collection containing a vertex from each component of the underlying space of the complex K, except for the one that contains V sub alpha 0. Okay, so the we have to take the topological space mod K, which is the underlying space of the complex K, and so we have to pick up a vertex from each component of this topological space, except for the one that contains the vertex V alpha 0. Okay, and that forms this collection. Okay, and this way we form this linear combination. Okay, and any element in this quotient group is given by this linear combination. Okay, good. Now any relative zero chain of K modulo K0 is a relative zero cycle, right? Relative zero cycle of K modulo K0 it can be seen that it is a fact, right? So so if you pick up a relative zero chain, then that is going to be a relative zero cycle. In other words, C0 of K comma K0 is Z0 of K comma K0. Okay, and using the arguments of reduced homology group in theorem 1, and using the arguments presented in step 2 of theorem 1. I think it's not the reduced homology thing. It's the zeroth homology group, where we showed where we computed the zeroth homology group of a given simplicial complex, and we have showed that's a free abelian group, right? So let me get back to theorem 1 and see if this is what we have done there. Right. Okay. Yeah, this is what we did there. So it's the zeroth homology group that we computed uh, in theorem 1. So using the arguments presented in the second step of this theorem, in the proof of this theorem in particular, um, one easily finds that the group of relative zero boundaries of K mod K0 is trivial. Okay, so we used, so for the ordinary zeroth homology, we use the arguments there to show that the zero boundary, the group of zero boundaries is trivial. So we use the same arguments here to show that the the group of relative zero boundaries of K mod K0 is also trivial. Okay, all right. Hence, H0 of K comma V alpha 0 is just Z0 of K comma V alpha 0, which is nothing but the group of relative zero chains on K modulo V alpha 0. Okay, this guy is free abelian and one has this collection of vertices or the elementary zero chains corresponding to these vertices where alpha is not equal to alpha 0 as a basis. Okay, but from theorem 2 of lecture 2, we know that the collection V alpha minus V alpha 0, where alpha is not equal to alpha 0, forms a basis for zeroth reduced homology group. Reduced homology group H0 tilde of K on K. Okay. Since each basis element, it's important to note that each basis element in the collection V alpha, where alpha is not equal to alpha 0, is in one-to-one correspondence with a basis element V alpha minus V alpha 0, where alpha is not equal to alpha 0. H0 of K comma V sub alpha 0, this guy, right? And H0 tilde of K have the same rank as free abelian group, and hence they are isomorphic. That is, H0 of K comma V sub alpha 0 is isomorphic to H0 tilde of K. This establishes the relationship uh, between the zeroth relative homology group with the zeroth reduced homology in the case in our case, where the subcomplex of the given complex is just a vertex. Now let us try to see, or let us try to address what happens in dimension greater than 0. Let us now see what happens in dimension p greater than 0. Okay, we dealt with the situation when p is equal to 0. Now hp of k comma v alpha 0 is equal to zp of k comma v alpha 0 modded out by b sub p k comma v alpha 0. Okay, let bp is an element of the group b sub p k comma v alpha 0. Then b sub p is a p chain on k and there exists a p plus 1 chain d sub p plus 1 on the same complex K, such that the difference bp minus del p plus 1 dp plus 1, this p chain is carried by the vertex v alpha 0. Okay, here p is greater than or equal to 1, right? So bp minus dp plus 1 is a p chain on K, right? Now there is no such non-trivial p chain carried by v alpha 0. Okay, since p is greater than or equal to 1. Okay, and v alpha 0 is a zero dimensional vertex, right? So there cannot be any non-trivial p chain carried by v alpha 0. Therefore, one immediately finds that b sub p minus del p plus 1 dp plus 1 is equal to 0, right? Which means b sub p is an element in this group of p boundaries on K. Okay, therefore we see that b sub p k comma v alpha 0 is a subset of b sub p of K. This is one result. Now, on the other side, let BP be an element of the group of P boundaries on the complex K. Then there exists a P plus 1 chain dP plus 1 such that BP minus del P plus 1 dP plus 1 is equal to 0. Okay. Then B sub P is, since this is 0, B sub P is trivially, not B sub P, I think I should write B sub P minus del P plus 1 dP plus 1 is trivially carried by B sub alpha 0. That is, BP is 0 on K set minus V alpha 0. Hence, one concludes that BP is an element of BP K comma V alpha 0, and that helps us conclude that B sub P of K is contained in B sub P K comma V alpha 0. Previously we have seen that BP of K comma V sub alpha 0 is contained in BP of K, so together we have BP of K comma V alpha 0 is equal to BP of K. This is our equation number 1. The equality of these two groups is numbered as equation 1. Okay, now let us have a look at the story of P of the group of P cycles. Okay, now let C sub P be an element of ZP of K comma V alpha 0. Okay, then del P CP is carried by V alpha 0, which follows from the definition of relative P cycles, right? So there is no, so what is this? This guy is a P minus 1 chain, right? There is no non-trivial P minus 1 chain in the form of del P CP that is carried by V alpha 0 for CP being a P chain on K. Okay, so it's easy to check. I would ask you to convince yourself that for p equal to 1 it holds. This case p equal to 1. Okay, when we have a zero chain, sorry, so that del p of cp is a zero chain. Okay, so work out this thing, and from this, since there is no such non-trivial p minus 1 chain, one concludes that del p of cp is trivial, is simply zero, and that implies that cp is a p cycle on k. Okay, therefore we started with this and we ended up with this, which means that zp of k comma v alpha 0 is contained in zp of k. It's trivial to show that zp of k is contained in zp of k comma v alpha 0, like we did before for the p boundaries, relative p boundaries. Okay, so this is our equation. Okay, and together with this imply zp of k comma v alpha 0 is equal to zp of k, which is our equation number 2, and 1 together with 2 imply hp of k comma v alpha 0 is equal to hp of k. So this is when p is strictly positive. Okay, and we have seen that for p equal to 0 we found that h0 of k comma v alpha 0 is the reduced zeroth homology group of the complex k, right? Okay, so that was example 2. Now our third example, example 3, where we deal with a complex whose underlying space is a square. Let K be the complex indicated below. We call this age E4, and these oriented two simplices as sigma 1, this one sigma 2. Each of them is oriented counterclockwise. Sigma 3, this is sigma 4. This is E1, this is E2, this is E3, this guy is E4, this is E5, this is E6, this is E7, and this is E8. Okay. Figure 1, complex K. It's a two-dimensional complex whose underlying space is a square. So the underlying space of K is a square. Let K0 be the complex whose underlying space is the boundary of the square, meaning that this boundary, this one-dimensional complex, okay, that's K0, okay, whose underlying space is the boundary of the square. This is K0. Okay, now let sigma is a two-chain given by this expression mi sigma i's sum over all i's from 1 to 4. Okay, so the sigma i's are the elementary two chains corresponding to the oriented two simplices, sigma 1, sigma 2, sigma 3, and sigma 4, which are all oriented counterclockwise. Okay, so let us denote this two chain by sigma. Let so so any two chain in our case can be written down like this, right? And let us take this two chain to be a two cycle, relative two cycle, z2 of k comma k0, okay, which is a relative two cycle of k mod k0. Okay, then according to the definition of relative cycles, delta 2 sigma is carried by k0. Okay, so let us try to compute del 2 sigma explicitly. So this is going to be I from 1 to 4 mi del 2 sigma I. This is m1. What is del 2 sigma 1? The boundary operator acting on the elementary 2 chain sigma 1. It gives us E5 plus E2 minus E1, right? And M2 times delta 2 sigma 2 is E6 minus plus E3 minus E2 plus M3 delta 2 sigma 3 is E7 plus E4 minus E3 plus M4 times E8 plus E1 minus E4. Okay, E8 plus E1 minus E4, E7 plus E4 minus E3. Good. All right, so this is equal to M1 E5 plus M2 E6, M2 E6 plus M4 E8 plus M3 E7. And then we have plus M1 minus M2 E2 plus M2 minus M3 E3 plus M3 minus M4 E4 plus M4 minus M1 E1. That is our equation number 3. Now, since we want delta 2 sigma to be carried by K0, which is the boundary of the given square, one must have these contributions to be identically 0, right? This should go away, this should go away, this should go away, and this should go away as well, right? So that we have contributions from the boundary of the square only. So we want M1 to be equal to M2, we want M2 to be equal to M3, and M3 to be equal to M4. Okay, so we therefore conclude that therefore the sum of these expressions mi sigma I, where I runs from 1 to 4, belongs to the relative group of two cycles of k mod k0 if and only if m1 is equal to m2 is equal to m3 is equal to m4. Okay, which means that in this expression uh, of the relative 2 cycle, all the coefficients should be the same. Okay, which means that this guy has to be a z integral multiple of this guy. Okay, some multiple m where m is in z. Okay, good. Since there are no three chains, since there are no three chains associated with the complex K, in figure 1, in this figure, there is no three chain, right? So B2 of the group of relative 2 boundaries on K mod K0 is trivial. This guy is trivial, hence one finds that H2 of K comma K0 is equal to Z2 of K comma K0 modded out by B2 of K comma K0. We have seen that this is isomorphic to Z, and hence this guy is isomorphic to Z. This is our equation number 4. Okay. Now, what's the story of the relative 1 cycles and relative 1 boundaries in this case? So remember we showed in the course of Algebraic Topology 1 that any one chain C of the complex K, of this complex K, any one chain in figure 1 is homologous to one chain C3 carried by the subcomplex K0 union E4, this one simplex. Okay, so in other words, by modifying the one chain, um, adding boundary components, one can push the one chain, the respective one chain of each of these three one simplices. Okay, so that the one chain is ultimately carried by this subcomplex. Okay, so we were introduced to this trick in the course of algebraic topology 1. Okay, so I'm not going over that trick. So refer back to lecture 7 of algebraic topology 1, and if you don't remember it exactly. Now, if C is a relative one cycle, okay, of K mod K0, that is, if C belongs to Z1 K comma K0, so that delta 1C is carried by K0, then one immediately sees that delta 1C3 is also carried by K0. Okay, remember here C3 is the one chain that is homologous to the given one chain C. Okay, where C3 is carried by this subcomplex K0 union this one simplex E4. Okay, so how do we see this? Indeed, in lecture 7 of algebraic topology 1, we obtained, I'm also writing the number of the equation where it was obtained in equation 24, that C3 is equal to C plus delta 2 A sigma 1 plus B sigma 2 plus D sigma 3. This is in our case equation number 5 for certain integers A, B, D in Z. Okay, so from equation number 5, by applying the boundary operator on both sides, we see that delta 1 C3 must be equal to delta 1 C. Why? Since delta 1 composed with delta 2 is identically 0, right? So therefore, since delta 1 C is carried by K0, delta 1 C3 has to be carried by K0 as well. Okay. If C3 had non-trivial value on E4, okay, if C3 had non-trivial value on this one simplex E4, delta 1 C3 would have had non-zero value on the vertex V, non-zero value at the vertex V. Vertex V is the point at which the two diagonals intersect. Okay, vertex V, which is not the case in hand, which is not the case, as delta 1 C3 is carried by K0. We have seen earlier that delta 1 C3 is carried by K0. Okay. Therefore, the the one chain C3 has to vanish on the one simplex E4. Therefore, one concludes that C3 vanishes on E4 and hence it is completely carried by the boundary K0. Okay. Since C3 is homologous to C, the one chain since C3 is homologous to the given one chain C, the one chain C that one started with is also carried by K0. One therefore observes that any relative one cycle C one cycle C of K mod K0 is actually carried by K0. In other words, okay, so one observes that any relative one cycle of C of the complex K mod K0 is actually carried by K0, right? What does it prove? Okay, in other words, in other words, z1 of k comma k0 is trivial. Why does it happen? Okay, I think it's a good time to take a break. I'll get back to the remainder of the case being handled in example 3 in the next segment. Thank you for attending the first segment.